So, good afternoon, everyone. Happy Sunday to us all. I pray wisdom, knowledge, and understanding the Lord will give to us. In Jesus' name. The spirit of excellence will not depart from us. So, we are starting with Econometrics question year 2020-2021. So, the first question is given the simple linear regression equation y equals to beta naught plus beta 1. We have the observations there for demand, quantity demanded, and price. So the first question says obtain the demand function. Obtain the demand function. This implies that we have to obtain, or rather find our regression line. Our demand function y equal to function of price plus our statistical term, stochastic term rather, so which can be mathematically expressed as this. The beta 1x plus our random error, but we need our estimated model. So we have our estimated model to be this plus beta 1 estimate plus beta 1 estimate x is our estimated model. I know we can all recall how we estimated from here to arrive at this from our applied general statistics, and we know our beta estimate will be equal to y bar minus beta 1 x bar, beta 1 estimate, and our y bar equals to summation of y over n, and we have our x bar to be equal to summation of x over n. Here our beta 1 estimate equal to this. Using our product moment formula, we have n summation xy minus summation x summation y all over n summation x square minus summation x all square. So using this formula from our computation, from the data, we have our y bar to be equal to 11.2, and we have our x bar to be equal to 13. We got our beta naught estimate to be equal to, when we press our calculator, we have our beta estimate to be equal to minus 0.8731, and beta 1 estimate, we have it to be equal to 0.9287. So which implies that our demand function, the demand function is y equals to minus 0.8731 plus 0.9287. 287x. That's all for our demand function. After computing our table, after tabulating our data and doing the necessary computations. So the B part, we have to calculate the coefficient of determination. So calculating the coefficient of determination, we are not using our normal, our coefficient of determination is the square of our correlation coefficient, and we are all familiar with the product moment formula and our EMR rank formula. But in this case, we will be using the deviation formula. Why? Because the C part of the question is asking us to compute, to obtain the standard error of the test of significance of each parameter in the above econometric model and decide appropriately when using two-tailed test. So instead of using product moment for this and going back again to use deviation for the other one, so let's use deviation formula for the both. So that was why we have our table more elaborated. So the formula for this is summation of the small case y estimate all over summation of y square. So to get our y estimate, that is using the regression model we got, we got our y estimate to be equal to minus 0.8731 plus 0.9287x for each data. So for the first one, we have minus 0.8731 plus 0.9287. Our x1 is 5.5. which happens to give us 4.2347. So we continue doing that until we get to the last observation, the y10 estimate, which is 0.8731 plus 0.9287 multiplied by 22.5, and this gives us 20.0226. Give us 20.0226. So we fill it into the column for the estimated values of y for each. So now to get our y, know that your y estimate lowercase deviation is equal to y estimate minus y bar. So y estimate square is equal to y estimate minus y bar all square. Also our y, derivation of y, is equal to y minus y bar, and this is equal to y minus y bar all square. So now we've gotten our estimated values for each demand, and we know our mean to be equal to 11.2. So to get our deviation of y estimate, that is 4.237 4.2347 minus 11.2. That will be giving us what we have here. So we do it for each observation and we take the square of it. So we have the total sum to be equal to 241.9256 all over. For y, we have our original y, which is our demand, to be this, and we have our mean to be 11.2. So we subtract 11.2 for each of the observations of y to give us our deviation of y, which we have here. Then we take the square of each of the observations. So we give us a total sum of 243.6. So thus we have our r square to be equal to 241.9256 all over 243.6. Using our calculator very well, we have our answer to be equal to 0.9931. 0.9931, which implies that our coefficient of determination is just 99.31%. By the time you multiply 0.9931 by 100, you have 99.31%. So the third question: obtain the standard error test of significance of parameters in the above econometric model and decision rule when it is two-tailed. So we have to take the standard error test for beta naught and standard error test for beta 1. So let's carry out our test of hypothesis. Let's do first for your beta naught estimate. Test of hypothesis. When it is a two-tailed test, our non-hypothesis beta naught estimate for two-tailed test is equal to 0. Or assuming it is tailing to the left or tailing to the right, then we use our greater than or we use less than. So our alternate hypothesis for two-tailed test to say beta naught estimate is not equal to 0. So our test statistic, that is the formula we use for the computation here, for standard error of beta naught estimate is equal to is the variance, root of the variance of beta naught estimate. Here our variance of beta naught estimate is equal to summation of our unexplained variation squared over n minus k multiplied by summation of x squared all over sum of the deviation of x squared. Here, note that our k is the number of parameters. Of parameters in our model. So we have variance of beta naught estimate to be equal to summation of their unexplained variation or square. We have our unexplained variation. How do we get our unexplained variation? Now our unexplained variation is equal to our original observation minus the predicted observations, that is the remnant, is our unexplained variation. Y minus y estimate. So from here we have our original y, which is our demand, minus our estimated observations. So we subtract each, then we have this, then take the square of it, because we need the square of it in our formula. So the total sum of the square is 1.6735 all over number of observations we have to be 10 minus number of parameters in our model is just 2, that is beta naught and beta 1, multiplied by summation of x square, that is summation of our original x, we have it to be 1970.5 over sum of the derivation of x, sum of the square of derivation of x, which is 280.5. I hope you know how we got the derivation of x, that is subtracting the mean of x, which is 13, from each of the observations of x. So by the time we work on this very well with our calculator, we have our variance to be equal to 0.000745. So mind you, we are working on a standard error, and our standard error of beta naught estimate is the square root of the variance, which is equal to root of 0.0000745, which is equal to 0.0273. That is our test statistic for beta naught. So our critical value we are all familiar with the critical values for statistical tests, which we always normally derive from our statistical table. But for the case of standard error test, we are not deriving it from the table. So the formula for getting our critical value is this: our beta naught estimate divided by 2. That's just it. Whatever answer we got for our beta naught estimate, we divide it by 2. So for our beta naught estimate, we have our answer to be minus 0.8731 divided by 2. So when we divided it by 2, we have minus 0.4365. That is our critical value. So please, sorry, there is an error here for the final answer we are going to get for this. The final answer we are going to get here should be 1.4689. 1.4689. So by the time we take the square root of 1.4689, we have 1.2119. So we've gotten our test statistics, we've gotten our physical value. So the next question they ask here is we should our decision rule. So decision rule. We already know the rule. Whenever our tabulated value is greater than our calculated value, we reject the non-hypothesis. So in this case now, we reject let's check our critical value and our test statistic. Which of it is more greater? You can observe here that our critical value, which is estimate divided by 2, which is equal to minus 0.4365, is lesser than our test statistic, which is 1.2119. Thus, what do? We do not reject. We do not reject the non-hypothesis. Thus, we conclude that there is no significant difference in the test. There is no significant difference. So that's it for the first parameter. Now we are asked to carry out the test for each of the parameters. So for beta naught now, though I'll still be taking the screenshot of each, sending it to you. So for beta 1, estimate, our test of hypothesis. For the non-hypothesis, you say beta 1 estimate is equal to 0 for two-stage test, and alternate hypothesis, beta 1 estimate is not equal to 0. Then our test statistic. Standard error of beta 1 estimate is equal to the root of the variance of beta 1 estimate. Here we have our variance of beta 1 estimates to be equal to sum of the square of the unexplained variation all over number of observations minus number of parameters enclosed summation of the square of the deviation of x. So So from the table, we have sum of the square of unexplained variation to be 1.6735. All over number of observations minus number of parameters. We have 2 parameters. Then summation of the deviation of variable x, 280.5. So working on this, we have it to be equal to 0.000745. Working on is taking the standard error, which is the square root of the variance for beta 1 estimate. We have it to be equal to 0.0273. So these are our test statistics. Now our critical value, just like we did for beta naught estimate, we also divide this by 2. We have it to be beta 1 estimate over 2, and we have our beta 1 estimate to be 0.9287. Dividing by 2 gives us 0.4643. So let's decide. Our decision variable for this now is since our critical value, which is equal to 0.4643. Let's see, is it greater than or less than our test statistic? We can observe that it is greater than our test statistic. .0273. So what do? We reject the non-hypothesis. Thus, we conclude that this error test is significantly different, or that there is a significant difference in the test. Thank you. Let's work on this first.